thank you to all the organizers. My talk is kind of on the same setting of the Charlotte's talk, and it will discuss about YB-semitrusses with a particular attention on YB-semitrusses, in which the associated solution is a bijective solution. Because the ambition of this talk is to convince that YB-semitrusses can be useful also in the setting of bijective solution and non-degenerate solution, the setting in which we know that skew braces do a really good job, but as Charlotte showed, we can use the structure monoid that has not the problem of that has not the injectivity problem. So I want to use this. I want to show you with this talk that YB-semitrusses can give new results even in the context of bijective solutions. Just an overview of what I'm going to talk about. I will start with the motivation, and I will recall, sorry about that, but some think about solution of the YB equation just to fix the notation, and I will give you again the definition of YB-semitrusses just for completeness sake, and then I will go into discussing the bijectivity problem. So we will see that for a YB-semitrusses based on the fundamental defined operation of the YB-semitrusses, we can immediately recognize if the associated solution is bijective. And then, as promised, the YB-semitrusses, Charlotte said that the YB-semitrusses are a generalization, so comprehend the skew braces, but we didn't prove that. And to do so, we will focus on a subclass of YB-semitrusses called the left cancellative semitrusses. In this case, we will focus on the case in which the additive structure is left cancellative. In this case, we will see that to prove that a structure is a YB-semitrusses will be easier. In this context, we will see that skew braces are example of YB-semitrusses that are left cancellative. And I will also present you an example of YB-semitrusses that are left cancellative, but in which the multiplicative structure is not grouped. So they really are not only skew braces. And then I will move to the main result of this talk, that is using the YB-semitrusses, we can prove that in the finite context, left non-degenerate solutions are bijective, even if they are right non-degenerate. And then I will move to the last section, that is the permutation YB-semitrusses, that is an attempt of generalize the concept of permutation group in the context of in the context of left non-degenerate solution. And here we'll see that we can slightly generalize the results that connect bijective solution and right non-degenerate solution when these permutation YB-semitrusses share some other condition. So what is a solution of Yang-Baxter? For me, a solution of the Yang-Baxter equation is always a set theoretical solution of the Yang-Baxter equation. My solution is not necessarily bijective, so it's a pair XR, where X is a set, it's a non-empty set, and R is a map, not necessarily bijective, that satisfies the braid equation. We will write the image of the pair XY with lambda x or y and rho yx. So I know that we saw different notation for that, like lambda and gamma and sigma and other notation. In this talk, we will use always lambda and rho. We'll say that R is left non-degenerate if the lambda maps are bijective, and right non-degenerate if the rho map are bijective, and non-degenerate if both lambda and rho are bijective. We will clearly use terms like finite when the set X is finite, or bijective for the solution when the map R is bijective, or involutive when the map R, where the square of the map is the identity map. So the idea behind the introduction, as Charlotte said, behind the introduction of the for the YB-semitrusses is just that we want an associative structure that allow us to recover somehow all left non-degenerate solutions. Later on, we will see that there is an algebraic structure called the Q cycle set that is in one-to-one correspondence with left non-degenerate solution. This structure was introduced by Rumpf, but it's based on two operations. None of them is associative. To do so, we consider an algebraic structure introduced by Thomas called semitruss, that is a tuple in which we have two operations that give to our set a structure of semi-groups, and a map lambda that somehow represents the skew brace relation. What I want to focus here that the class of semitrusses is a very wide class. In fact, if we have a ring, just a ring, right? So if we have two operations and the distributive connection between these two operations, this ring is a semitruss. So we cannot expect that for every semitruss we can have a solution of the YB equation in the same flavor as a solution associated to a skew brace, for instance. So we want to focus on a special class of semitrusses that give us all the elements to define solution of the YB equation in the same flavor as is done for braces and skew braces. So the definition of a YB semitruss is worth to recall this definition, just because it's the core of this talk. Is a tuple, is a tuple A plus circle lambda and sigma. This is a YB semitruss if A plus circle lambda is a semitruss. So we have this kind of distributivity between the circle operation and the sum, and we have that sigma is a map that maps all elements of A into maps that we will denote in this way. We will denote this like sigma sub A, such that they satisfy some property. So they are for if we look at YB-semitrusses from the perspective of skew braces, we can see that these are really, natural requests. So the first one is that the lambda map, we want to work with left non-degenerate solution. So what we want is that the lambda map are bijective, and in particular, we want that these are automorphism of the additive structure. Moreover, we want that somehow lambda is an homomorphism between the multiplicative structure and the automorphism group. So we basically want that lambda A or lambda B is just equal to lambda A circle B. Then, if we think about the property that are satisfied by the skew braces and the lambda map, we see that there is a strict connection between the spherical operation, the sum, and the lambda map that we still want to have here. So we ask that A plus lambda A of B give us the multiplication, the circle operation between A and B. Then we somehow want, we know that we started with braces, so a situation in which the additive structure is abelian. So we do not want an abelian monoid, but we want somehow the possibility to change the place of elements in the additive structure. So we want that A plus B. To do so, we will use the sigma map. So A plus B is just B plus sigma and B of A. And the last property is that sigma will be an anti-homomorphism between the additive structure and the endomorphism monoid. So we have that lambda A is an endomorphism of the additive structure, and rho A plus B will be equal to rho B, rho A. And finally, we want a kind of compatibility between these two mapping. So we want that lambda A sigma B is just equal to sigma lambda A of B lambda A. So somehow we can change place between lambda and sigma. And this definition that I see there are a lot of conditions, but we will see that in some with extra properties we can ask less. We have less things to verify to prove that something is a YB-semitrus. But if we have a YB-semitrus, then we can define a rho map in this way. Let me just say that this is not so a so crazy definition as it can seem. Because if we think about the connection between the two components in an involutive left non-degenerate solution, then the rho map is just lambda inverse lambda A of B of A, where this sigma map somehow seems to be like the identity. Actually, this is in general the case, but this explains or this shows from my perspective that this is not so unexpected definition. And in this case, then we can say that this is a solution what we expect. So if we have A plus circle lambda and C YB-semitrus, then the map R sub A from a square to a square, defining that us associate to a pair A, B, just lambda A of B, and this rho B of A is a solution of the Yang-Baxter equation is clear is because of the assumption that lambda is bijective. This is left non-degenerate. Moreover, Charlotte mentioned the derived solution of the for a left non-degenerate solution. We can always define derived solution. In this case, the connection between the solution associated to a Yang-Baxter semitruss and its derived solution is really, really strong, and we have that R is nothing else but phi inverse. I will tell you in a moment what phi is. Phi inverse is a phi where SA of AB is just the derived solution. As if we compute the derived solution, this is just B comma rho sigma B of A, and phi is just the map given by A and then lambda A of B. So what we can see that this is P. So with this relation between the map R and the map S, we can see that we can answer the question when a solution associated to a Yang-Baxter semitruss is bijective. In particular, we have that if A is a YB-semitrusses, clearly, if I write A, I just mean A plus CFL lambda and sigma. So if we have a YB-semitrusses, RA is and RA is associated solution, then RA is bijective if and only if SA is bijective. And if we recall that SA is just the derived solution, so it's defined in this way, it is easy to see that this simply means that SA is bijective if and only if SA is right non-degenerate, that means simply that the sigma B maps are bijective for every B in A. So if we want to focus on YB-semitrusses in which the associated solution is bijective, we just need to restrict ourselves to that structure in which sigma B is all sigma B are automorphism of the additive structure. So it is natural to ask ourselves, okay, we know that if the sigma B maps are bijective, then this means that the associated solution is bijective. And what I really want to see is what happens for the inverse solution. So there is somehow a YB semitruss that allow me to construct the inverse solution. The answer is yes, as you can expect, and is the following. So if I have A plus circle circle lambda and sigma YB semitruss with sigma B bijective for any B, then we just saw that RA is bijective and its inverse is given by R inverse of A, is given by this relation. This is not difficult to see that, and we can see is a sigma inverse of A. So we really use the fact that sigma are bijective. So sigma inverse of A, lambda A of B, and lambda inverse of sigma inverse of A, lambda A of B, just A. But we can say more. We can define, if we put lambda bar of A equal to sigma inverse of A, lambda A, and sigma bar of A just equal to sigma inverse of A, then we can see that A plus of, here I mean that A plus of B is just B plus A, circle, and we need this inversion for technical reason. Lambda bar and sigma bar is YB semitruss, and its associated solution is, we can compute this, and this is indeed the inverse of RA. In analogy with what happens for skew brace, we call this the opposite YB semitruss. Let me just tell you that in case in which the YB semitruss is a skew brace, this is exactly the opposite skew brace. So, okay, can I continue? Okay, so the condition to have YB semitruss seems really a lot. So we can restrict ourselves to the case in which the additive structure is left cancellative. In this case, if we have if we have a semitruss, so we have this kind of distributive relation, sorry, and we have that all lambda maps are bijective, then, and there exists an element that allow us to write A circle B has lambda A of B times something. That is something that we expect because it's something that happens for skew brace. Then this, then we can prove that in this case there exists a unique. The fact that is unique is because of the left cancellativity, a unique map sigma that gives our semitruss the structure of a YB-semitrus. And in particular, if we call this element X here has rho B of A, we know that there is one for any A and B, then in this case, we have an explicit representation of the sigma B maps in this way. This is just lambda B rho lambda inverse A of B of A. So we see that we have less condition to verify. In particular, if we have this condition that links together the sum, the circle operation, and the lambda map, then we have free the sigma map. So, and as an example of, as an application, let me say, as an application of this characterization for left cancellative semitruss of left cancellative semitruss, we can see that a skew brace is in particular a YB-semitrus as promised. So if A plus circle is a skew brace, which, just to a quick reminder, this means that A plus and a circle are groups, and A circle B plus C is just A circle B minus A plus A circle C, then we can prove that A plus circle and lambda satisfy the condition of the previous result, in particular, give us a structure of YB-semitrusses. So in fact, we can see that we can note that since A plus is a group, in particular is left cancellative, then we can observe, if we call this element here lambda A of C, then we can observe that A plus lambda A of B is just A minus A plus A circle B, that is just A circle B. So also the other condition is satisfied. And then if we recall that inside the skew brace, if we put rho B of A just equal to, a way to write this is this one. This is a way to write the second component of the solution associated to skew brace, where the bar just means that I take the inverse of the element inside the group A circle, then lambda A of B circle rho B of A, one can prove that this is equal to A circle B. So this is actually our X that we need inside the definition. So for the previous result, we have that there exists a sigma map such that, so there exists sigma such that A plus circle lambda and sigma is a YB-semitrus. We can say more. We know that these sigma maps are bijective because the solution associated to a skew brace is bijective. But if we can compute these sigma maps, so sigma B of A is nothing but minus B plus A plus B. But the question is, all left cancellative YB-semitrusses are skew braces or something like skew braces in which the additive structure is a group, in which the multiplicative structure is a group, because there is a generalization of skew brace called left cancellative left brace, in which we have a left cancellative semigroup and as additive structure and as multiplicative structure the group. The question is, we can have something different? The answer is yes. I want to give you a very easy example just to convince you that this is the case. So consider a set of 4 elements that we call 1, 2, 3, 4. And then we want a left cancellative semigroup. We want to define here a left cancellative semigroup. The easiest thing that we can do is to define that A plus B is just equal to B. So we can define, look at A as a right zero semigroup. So any element in A acts like right zero. Right. This is a left cancellative. This means that A plus is a left cancellative semigroup. Then the other condition that our YB semitruss has to satisfy is that A plus lambda A of B is equal to A circle B. And the only thing that we can do, because this is just equal to lambda A of B, then the only thing that we can do is to define A circle B equal to lambda A of B. And I will give you an explicit definition of the lambda maps that you need to trust me that satisfy the requirement of or satisfying lambda A, lambda B equal to lambda A circle B. So lambda 1 is equal to lambda 2, and is equal just to the identity, and the other map is lambda 3, lambda 4 is equal to 1, 3, and then 2, 4. So what else we need? So we define an addition and multiplication, the lambda maps, and we can define the row map. The easiest row map that we can define is just equal to B. So in this case, we can verify that all the requirements for being YB semitrusses are satisfied, and in particular, we can see that A plus circle lambda and sigma is a left cancellative semitruss. YB semitruss, sorry. YB semitruss. What I want to show now is that if we look at A1 circle 1, this is by definition just lambda 1 of 1 that is equal to 1. So 1 is an idempotent element, but 2 circle 1 is lambda 2 of 1 is again equal to 1. So this means that a circle is not a group. So we have an example of a left cancellative YB semitruss that is not a skew brace because the multiplicative structure is not a group. So we are now ready to state the main theorem and to see the basic idea that lies in the core of the proof. So if we have left non-degenerate solution, then R is finite. So X is finite. This is a very essential assumption. So if X is a finite left non-degenerate solution, then R is bijective if and only if R is non-degenerate. The implication are bijective implies non-degenerate. It was proved by Castelli, Catino, and Stefanelli, and the proof is based on an algebraic structure that generalized cycle sets introduced by Rump called Q cycle sets. And the other implication, for the other implication, instead, we really need the notion, at least for our proof, we really need the notion of YB semitruss and the fact that the structure monoid of left non-degenerate solution is a YB semitruss. So just to have an idea about what is a Q cycle set, I promised you this. So a Q cycle set is a set with two binary operations that satisfy these three conditions. The two operations are not associative, and we can see that this is a generalization of the notion of cycle set. I just recall you that X is a cycle set. X with a binary operation is a cycle set if it satisfies x dot y dot x dot z equal to y dot x dot y dot z. And now it's easy to see that if we have if we have a Q cycle set in which the dot operation and the colon operation coincide, then we have a cycle set. So this is a generalization of cycle set, but this is more, right? There is a one-to-one correspondence, as happened for cycle set. There is a one-to-one correspondence between left non-degenerate solution and Q cycle set. And this correspondence is really, really clear. So let me give you just the main idea of this correspondence. So if X dot column is a Q cycle set, by assumption, we know that the map that has no name here is bijective, then we can consider its inverse. So for us, lambda inverse X of Y will be equal to X dot Y. So maybe we can call this map F X Y and taking the inverse, and then we can define rho Y of X equal to lambda X of Y column X. And the map R defined in this way, so using lambda X, Y and rho Y X is a left non-degenerate solution of the Ambaxer equations. The converse, so if XR is a left non-degenerate solution, then we can define X times Y equal to lambda inverse X of Y, and X column Y just equal to rho lambda inverse Y X of Y. And in this way, we can prove that X with respect to these two operations is a Q cycle set. Just a quick remark, the fact that we define the second component in terms of the inverse of lambda is why, in my opinion, the Q cycle set seems not to be so good to distinguish the concept of right non-degenerate solution and the concept of bijective solution. So the core of our proof is based on the fact that the structure monoid is YB-semitrusses, but actually the structure monoid is more. In fact, we can define in a natural way the concept of YB-semitrusses as a strong and graded. So if we can divide our semitruss as a disjoint union of subsets, and they satisfy the relation such that an plus am is just equal to an plus m, and all the lambda and sigma maps are degree preserving. So in this case, we have the definition of a strongly n-graded YB semitruss. We can see that the structure monoid is the structure monoid of a left non-degenerate solution. As we saw in Charlotte's talk, this is a YB semitruss, but this also has a natural strongly n gradation, and in particular the generators are the element of degree 1. So this is this means that all we can say about n-graded YB semitruss can be translated to a result for finite left non-degenerate solution. So the basic the things that we know about involutive solution and the connection between being right non-degenerate and non-degenerate until now was that we knew that any finite involutive left non-degenerate solution is non-degenerate. This was proved by Rump using cycled sets, and was proved by Jespersen and Okniewski using I monoids. Moreover, Sedot, Jespersen, Verpin, so they proved that under very strong assumption, that is, if we have a solution that is left non-degenerate, that is non-degenerate, and such that lambda x is equal to lambda y if and only if x and y are equal, then in this case we can prove that this solution is bijective. We can slightly generalize these by considering non-degenerate solution that satisfy, instead of these, just lambda x, lambda y, and rho x equal to rho y implies x equal to y. We can adapt the more or less the same proof that they had to prove that also in this case, this solution is bijective. And finally, Castelli, Catino, and Stefanelli proved that bijective left non-degenerate solutions are right non-degenerate. So using so the core idea to prove the converse of the previous result is looking at the so-called diagonal map. So the diagonal map is defined in this way. So it's lambda inverse x of x, and was called, if I remember well, by Leandro as the T map. This really plays a role. In fact, we know that we can prove that if we have a non-degenerate YB semitruss, then the Q map is injective. We can prove that if the Q map is bijective, then RA is bijective. This was proved by Rump, and we can mix these two results to say that an n-graded YB semitruss with all the homogeneous component finite, in particular, if we have as a YB semitruss the structure monoid of a finite left non-degenerate solution, then in this case, a solution is right non-degenerate, then it is also bijective. So so instead, the converse is, as I said, is based on a characterization given by Rump for bijective solution, and I want to underline that really bijective really plays a role in its proof. So for bijective solution, Q being bijective is equivalent to R being non-degenerate. And then we can adapt somehow the same proof given by Castelli, Catino, Stefanelli to prove that also for YB semi-truss, the implication holds. So just some remark. I want to say that it's worth mentioning that the result that a non-degenerate YB, if we have a non-degenerate YB semi-truss, then the Q map is injective, shows that actually we can really look at the solution associated to a YB semi-truss splitting what means for the YB semi-truss that for our solution to be bijective, and which property are based on the fact that the solution is non-degenerate. Moreover, we can also underline the fact that the assumption that the solution is bijective or non-degenerate is really important here, because because we can construct a really easy solution that is that has the Q map bijective, but that is neither bijective nor right non-degenerate. And this is a really easy example, is the solution RXY that maps the pair XY in YY. This solution is clearly left non-degenerate because the lambda map is the identity, but is not right non-degenerate because the row map is it's the map that maps row Y of X into Y, is something that also Charlotte noticed. But it's easy to see that since lambda is the identity, the lambda X map is just the identity, then the Q map is just the identity again, and so it's bijective. And just to finish with the definition, with just the idea of the permutation YB semi-truss that extend the concept of permutation group, we just introduce this new name for a YB semi-truss. We say that the YB semi-truss is non-degenerate if its associated solution is not degenerate, just to be brief. And so this means that we are we're just looking at the map, the row map being bijective, and I recall you that the row map row B of A is just lambda inverse lambda A of B, sigma lambda A of B of A. And so we are assuming that all these maps are bijective. So if we have a YB semi-truss, we can consider this set, and we can prove that this we can define a sum circle operation, a lambda map and a sigma map in such a way this structure as a structure YB semi-truss in the case in which our YB semi-truss is non-degenerate. In particular, we can prove that that we have a YB epimorphism between the our YB non-degenerate semi-truss and this set that we can call the permutation YB semi-truss. We can also notice that here it's inside the definition of YB semi-truss with respect to the definition of a permutation group, we added a dependency on the sigma map. Actually, for non-degenerate solution, we do not really need to take also into account the sigma map, even in the case in which the associated solution is not bijective. So we can have a bijection between the set GA and the set just of the pairs of lambda A and rho B. But I think that it's worth to look at the permutation YB semitruss in its full with this full definition. So in this case, so if we have an undegenerate YB semitruss, we can slightly generalize the correspondence between being bijective and being right non-degenerate. So we have that GA is a YB semitruss. We have that the multiplicative structure of this semitruss is a cancellative monoid, and it satisfies the left and right order condition. Moreover, we have that under the assumption in which for every A in A, we have an element B such that lambda A lambda B is equal to the identity and rho B rho A is equal to the identity, then the associated solution is bijective. And we can say more. We can say that the permutation YB semitruss is indeed a skew brace. Moreover, we can notice that these extend the case in which the lambda A and rho A maps are of finite order, which happens, for instance, when the solution is finite. And finally, we can see that if we look at the semigroup generated by the lambda and the rho, then if in the case in which this semigroup is indeed a group, then also in this case, the map R is bijective. And this more or less is what I wanted to say. The only thing that I want, and I'm going to finish, the only thing that I want to say is just a question. What we can say about the infinite case. So what is known is that there is an example of an involutive left non-degenerate solution that is not right non-degenerate solution. This example is due by Rump, but we really do know nothing about the other way around. I mean, what happens, it is possible to construct a solution that is left and right, clearly infinite, that is right and left non-degenerate, but it's not bijective. And with this, I thank you.